Start here in a moment, but it's just a quick sound check, make sure everything's working, and let you know that if you're listening to this recording, it's not the live event. I failed to hit the record button, so I'm re-recording it using the same material, and I'm going to acknowledge the chat and input I got from the live audience as appropriate through the presentation to reflect what we actually did during that. But it won't be quite the same and dynamic part of it, but I'll be referring to the chat window and moving it along to reflect what was happening during the original meeting. But the other part is in the recording. If you're using the Adobe Connect server to view the recording, you'll be able to pull down the download of the slides, which is just to the right of where my green arrow is. It should be kind of right center on your screen. If you highlight that reliability distribution slide set PDF line, it's a download file will become available, and you'll be able to download it directly from their server. And I usually remember, not always, will post this also either to SlideShare and or to the website where this recording is going to be housed. So it should be available. If it's not, let me know and I'll get you a copy of it. Those that have seen my other presentations know that the slides are interesting, but they don't contain a lot of information, but they may still be suitable if you want to just listen to the recording and then view the slides at your own pace. So with that, let me go into a little bit more about reliability distributions and the data that we use to derive those. I spent a good amount of time developing material about the data and where it comes from. And then what do we do with this? How do we use distributions to do it? And it's something that we need to do on a day-to-day basis to answer a range of different questions. And we'll discuss that. Plus, I'll bring up this download slide near the end of the presentation also. Hopefully I remember to do that. So let me move over to the slides. And really the first question is, well, I want to add one other note. I put this reminder in here for me. I'm working on a whole website called Ascendo Reliability, and it's intended to be an educational or professional development hub for reliability professionals. And the webinars will be are recorded. The ones that are recorded are stored there. There's a couple of ebooks. There's a 15-part email-based or text-based series on learning reliability engineering. And I'm working on adding more and more material and other people's courses and content and so on to make it a standalone professional development site. One of the things I'm interested in, and if you have any interest, let me know, is to create a podcast series and talk about the different aspects of what we deal with on a day in and day out basis as reliability professionals, or as we work to create and design and build and deploy reliable systems. So watch for more coming out about the Ascendo site. So reliability distributions. This is not a topic that you talk to your neighbors about willingly, or unless they happen to be statisticians. You don't. It's not the leading topic at a cocktail party or a gathering of your relatives or friends. Yet it's something that we use almost day in and day out, or all the time, I should say, to answer questions based on the nature of variability that occurs in what we deal with. Reliability distributions and reliability statistics in general, I used to try to build on what previous people have used or have learned about statistics, their undergraduate statistics course. And I found that that doesn't work very well, as I'm sure you have, because most people did not enjoy that class. And even though they've heard of the normal distribution and probability and statistics, it wasn't one of their best subjects or favorite subject. A few people did well with it, but didn't retain it, don't tend to use it on a regular basis. Um, Reliability is a little bit different, right? We're dealing with stuff typically that goes from time zero when it was created or put into service until it fails, so to plus infinity. Whereas the normal distribution, which is useful for quality control and process capability and all kinds of other applications, goes from negative infinity to plus infinity. So it's a little bit different. Many of the same concepts apply, but it's, what is it that we're dealing with? It's a slightly different set of materials. So life data is a common term we use to talk about reliability data. But what is that? It could be the counts of failures. It could be the time to failure. And, I'm getting comments that it's, time to failure data, maintenance repair data. There's a database from NERC that, Gene, you've talked about, infant mortality data, early failures. It could be cycles to failure, pages printed, it could be miles driven, all kinds of different things. What you see in the comments is it's typically something to failure, or even a degrading data, as Justin points out, is showing the change in performance over time, generally leading to failure at some point. So there's a wealth of different kinds of data, and it often depends pretty heavily on how we define failure. What is it that we call a fault or a failure? So caution is, especially if you're getting data back from the customers, is what they define as a failure and causes them to complain or send the product back is closest to what we're really interested in. If it doesn't meet their expectations, something's wrong. Now, it might be the product itself is not suitable for them. That could be part of that, but also just if a product's working as expected, it will be used slightly differently by different customers. It'll be under different kinds of stresses. It'll have all kinds of variation that will cause the time to failure, even for a common failure mechanism, to have a significant amount of variation. And if you look at human mortality, it gives us that kind of, I'm sure it's written down someplace. It's required to show a bathtub curve during a reliability presentation, especially about distributions. And this is about the closest I've ever seen to a system, a human in this case, and their change of failure rate over time. And so the vertical axis is a failure rate. So basically a 1 in 10, 1 in 100, 1 in 1,000 chance. And it's a scale, I believe it's in units of years. So you have a 1 in 10,000 chance to fail, to pass away when you're 10 years old, which is kind of this low point on the curve. 10-year-olds are nearly invincible, which is probably a good thing. But there's a little bit of a jump. If you look at the detailed data, there's a little bit of a jump about the driving age for most parts of the world. This was in the UK. So between 16 and 18, there's a step function here. And then it just goes to a relatively slow wear out pattern here, where every year we have a little bit less chance of getting to the next year. And this is a way to present life data. It's a failure rate over the age of the system, but it's complicated. There's many different elements that make up this. Now, when we deal with the system, and many medical professionals would look at just cancer, just the risk of accidents, just a particular line that would be a subset of making up these top lines that are shown here. But it gives us a sense of the overall performance of something. And this is a hazard function plot or a failure rate plot would be another term for it. But it gives us a sense of what's going on with the life data that we're dealing with. Now there's plenty of things, there's types of data, and this alludes to the attribute data, the count data, number of blemishes per panel or number of defects in a lot on a pass-fail type basis, or it could be variables data, length, time, cycles, miles, that kind of stuff. But there's also different ways we gather information about what's going on, and certainly there's plenty of issues with that. So in your experience, and I asked the live audience for, what's your experience with this? What could be wrong with this? And I got quite a few different comments. Everything from that it's incomplete, it's inconsistent, and that could be clerical errors, it could be a measurement error that's built into the numbers. It's also, when was the suspension? When did those systems that we don't know failed, are they still working? Or were they decommissioned and put out of service, and we didn't know about that? They didn't fail per se, but are they still operating as expected? Small samples, interval data instead of actual data, could be month shipped, month return versus hours of operation. All kinds of peculiarities to the data that we get, but it's also oftentimes the data is not exactly as Jeff points out in the comments. It's not the data that was intended to be used for reliability analysis. So spares data may give you an indication of what's being repaired within a system, and that may be tracked simply for a warehouse type function or a repair ordering of spares type function, whereas the rate of those turnovers may be very informative for us as to what's failing in our products. So that can happen as we get a alternate way to find the data that we're looking for. What it comes down to is, we've got all these different kinds of data, and they have lots of warts and issues and problems and so on. Yet we're still then asked a bunch of questions to translate that data, or the data we wish we had, into information. And so what kind of questions are you asked on a regular basis that is related to a reliability aspect of what we do? So a few comments here, is what's the warranty? How many failures should we expect? Will it last long enough? Are we missing opportunities? Is there a way to optimize the balance between repairs and warranty and reliability of a design? Is there, but the other part of this is also what's failing. What kind of items are failing? So beyond just the time to failure, we also almost always need to know, well, what failed? So in general, we have a couple basic questions that we get asked. Is the product good enough? Is it going to meet our expectations, our customers' expectations? Is it going to meet the warranty targets? And is it going to be profitable? Is it good enough? And this may be based on previous field data, on historical data, on all kinds of different things, but it's a question that we try to extract and have some basis in order to come up with a number. Another question we get asked is kind of is it better than something else? I saw that actually as a goal for a product one time, is it has to be as good as or better than the previous product. Well, they didn't really know how good or bad the previous product was. It was really hard to know if you're better than. Yet it's a typical kind of question. Is the cost reduced version of this product as reliable as the previous product, the non-cost reduced one? Is the new features improving or detracting from the reliability performance of the product? It's comparison type questions. And you also see it in comparing two vendors, looking at two components to solve a problem in a design. which one is more durable? That might be a better than type question. In the world of maintenance and asset management and in more complex systems, we also need to know the number of spares or the replacements. How many times do I have to take this in for repair? This relates obviously then also to the cost of ownership, which may be a more important feature than the initial purchase price for your product. So there's these kinds of questions that we lean on reliability distributions to help us answer. So how do you get the data you need, right? So we know that we have these kinds of questions, and there's a lot of different issues with the existing data we have, but how do you get what you need? So as one example, we'd had years ago, I was working with a colleague that was investigating fans and the reliability of the range of different vendors we were dealing with. Now, we knew anecdotally that some vendors were better than others, but we had no real data on that. And this was a range of servers and desktop computers that use cooling fans. And so what Mike did is he went to the repair centers and looked at their stocking and restocking orders for particular vendor fans, the particular part numbers, and very quickly found that a handful of vendors were used proportionally more often than other vendors' part numbers for their fans. And he worked out the volumes and number of exposed units and so on. But some fans had 3 and 4 and 10 times the failure rate if you translated a order of a new fan, a spare part, as an indication of a failure. And so we had some evidence now. It's not perfect by any means, and it certainly wasn't gathered for time to failure analysis, but it did give us a very clear indication that this one vendor was markedly better than the other ones. So we spent time with them to figure out what they did better or different so we could incorporate it across our designs, but also just get a sense of what do we look for when we specify a particular fan? What are the attributes that make it a reliable one? So that was a creative use of finding data. We used very simple analysis techniques to understand it, but it gave us the information we needed to answer the question. So one of the things we do with a pile of data, we gather up the information we think we need. We get sometimes a very large pile of numbers. In one case, I was asked to take a look at the weather conditions in California for an outdoor application, and they wanted to understand where the testing they were planning on doing and the design for the environment, was it suitable? Were they on the right track for what they would expect to see in outdoor conditions? So I went to the NOAA website, National Oceanic and Atmospheric Association or agency, something like that. And they have weather station data, and they have wind speed and rainfall and high temperature, low temperature, all kinds of different information. And so this is an example of just gathering daily temperatures. And as a few people have pointed out that my handwriting couldn't hide the fact that I wasn't spelling Celsius correctly. But these are daily, I think they were maximum temperatures for about 24 different locations in the area where they expected this product to be. And it's a basic histogram. Now, it's not quite normal. It's a little bit skewed, and there's lots of data behind this plot, but it's immediately useful just as it is, as we can say, count what proportion of days we saw 30 degrees C or less. And that might be 80% of the days saw that as their max temperature or less. What the average is fairly obvious, and somewhere around a little less than 20 Celsius. Very few days we had up over 40 degrees C, yet it gave them a sense of what was the nature of the weather that they would expect to see, the temperature range and so on. We ended up using it to find a 90th percentile and to give us a sense of judging our environmental testing to what proportion of exposures it would have to higher or lower temperatures, for example. We did similar work with other data sets as appropriate as stresses into the product's design. But it's a very simple plot, yet it is a distribution. It's empirical. I don't have to fit a curve to this, but I can use it to answer questions that are relevant for what we do in our work. Now, warranty return data is often very convoluted and messy and not necessarily set up for reliability analysis, but even something as simple as month manufactured and month return can give us some insights to what's really going on if we treat it well. So one example here is a histogram of the count of returns per month. So what do you observe here, right? George, you're mentioning that something's going on around month 6, right? We see this steady increase in the count of failures. Bimodal is another way to look at it. Brian, now there's no more data off to the right. This is we had about, I think it's a year's worth of data or 11 months worth of data. And Adam's onto something here is that this doesn't include time to failure. We don't know, let me pull up my arrow here, we don't know if in this particular month, with 15, 16 returns that appeared, if those were all early failures that had just been shipped, or were those failures from units that had been fielded for years. It's not apparent in this kind of graph. The other anomaly that we see is this increase in the latter months is probably more a reflection of the number of shipments we made and a type of failure that was occurring. So investigating like a Pareto of this month, the second month versus the second to last month may show a very different proportion of types of failures or types of reported failure modes. Will give us indication whether we're dealing with early life or end of life wear out mechanisms. But this plot, while showing us the number of returns we're receiving per month, isn't being normalized for the number of units that are at risk, and much less than what's the age of those units. So it gives us a picture of roughly how many units to expect coming back in the door, and we could probably take steps to normalize this for the number of units available to fail. Yet it doesn't really give us a lot of rich information about what's going on. So let's take a look at, histograms as a common plot. It's not necessarily my favorite, but I almost always use it first. Weibull plot is another very common one, and I know that a number of other people are looking at that. But one way to look at field data or time to failure data is a Weibull plot. And I know prior to the start of the discussion, a number of people mentioned they used Weibull distributions and Weibull plots fairly often. The cumulative distribution function is probably my favorite. I use it all the time. But it takes the basic data that we had previously and it allows us to, let me get rid of the annotations I got on here, just a second. So that if you take each unit that fails and set them at time 0, and use this vertical bar as 0 on the timeline, that the oldest units would be running the longest. And the arrows at the end of these lines mean at the last time we checked, they're still running. But these two units were shipped at some point later in time than the top two, and they're still running. But they just haven't run as long because they got say 2 months delay in getting started. And then every now and then we'll get information about a failure. And so this unit may have started at the same time as the first two, but it failed. And now we have a time to failure piece of information, along with the previous 4 units that have not failed yet. Those would be suspended or censored data, write censored data. And as we go down the line, as we collect this information for each of our products, we either have a product that's at risk and hasn't failed yet, or it's a product that has failed. And while this isn't a practical way to do the analysis, it illustrates the point that we're starting everything at 0. It could be the shipment date, it could be the install date, it could be put into service date, commissioning date, something along that lines. And some products we have hour meters, for example, on them, or odometers. They then give us how much use it actually has had, and we could use that to find the 0 point. But we take that kind of data, and once again, let me clear up my annotations. And this is one way to record field data as it comes back on a month-to-month basis. But let's say in January we ship 568 units. And right away in January, say a week or a few days later, or immediately, we get 2 failures. Now those 2 failures could only have come from January because that's our initial shipment. And then in February, a month later, we receive 37 more failures, but the bulk of those are from the January shipment. The February group has another 479 units, but only 3 of those came back right away. And so this is called a Nevada plot, and it's a way to organize the returns you're getting, but then associate them with when they were shipped or when they were put into service. And it gives us a way to tabulate the time to failures. Now, Weibull++ allows you to basically cut and paste this right into their software and create Weibull plots. It's a bit harder with Excel to convert this to time to failure data, but it gives us all the information we need to do that. And I think it's called a Nevada plot because if you squint and tilt this 90 degrees counterclockwise, it has roughly the shape of the state of Nevada, but it doesn't really work for me. It's just what they're called. The essence, though, is that we want information that tells us the time to failure based on when it was put into service, whenever we can. Plus, if you tally, let's go down here to the October one, we've had 2 failures of the units put into market or put into service in October. So that means that there's 935 that have not failed yet. Now they're only 2 months old, and only 2 have failed in the second month, and 935 have not failed in the second month. So it gives us what's failed, the time to failure data, and what's still at risk, what has been censored from in the data set. Now both those pieces of information are critical when we create a Weibull distribution plot, the CDF plot. So these blue dots represent the failures, and in the construction of this plotting is included the censored data, the ones that haven't failed yet. But overall, it looks like that we're at about 10% failures, or I'm sorry, looks like that's 20, so 15, 16%, somewhere in there, 18% failures after about 10 months. 10% failures at roughly a year, or a little longer than a year. So this plot provides the proportion that have failed versus time, in this case months, and it ranges from 0 or close to 0 to 1 at the high end. And so eventually everything will fail, and what we're interested in is not only the slope of this line, is it increasing or decreasing with time, is it indications of the early life type failures or wear out failures, but also when do we expect to see the failures? When are they about to occur? Now, fitting this to a Weibull distribution, which this software does fairly quickly, I get a beta, which is the slope, of 1.1. So there's a slight increase from month to month of the chance of failure. It's on a wear out path, but not dramatic. The eta, also called characteristic life, gives us the point at which 63% of the units have failed. Now, we haven't achieved 63% yet, but that gives us roughly, I think this is the 50, so 51 is a little bit above that, and that gives us a point on a line plus the slope, and we can create the entire curve. So this is a log-log plot, but it gives us a fitted line to a curve. It's regression against this particular formula, a Weibull distribution formula. So I find this plot really useful to explain what's the nature of the changing rate of failure. So one of the things that can happen, and as you know, there's multiple failure mechanisms that are involved, and it allows us then to plot the failures that we're seeing and to detect if there's a change in the nature of the failure rates. So let's say that a motor or a compressor has had no failures up until about 10 to 12 months, and then the failures follow this line. So it takes kind of a hockey stick approach or look to the line. Now, it's very likely that the failures that make up these failure points are different than the ones that are early failures, right? Ideally, you plot a single failure mechanism, but in this case, we have just the system level ones. Now, it may make sense to break this apart into the different failure mechanisms. So a motor wear out may have a very high beta, very high slope, and be masked by things that are occurring earlier in the program, say factory escapes or installation damage induced failures. That once we solve those, we still have these other failure mechanisms to deal with, but it'll give us a change in the way the overall graph will look. So that's one look at the data. And this one I drew all over, so I'm going to clear off a bunch of these. So this is the same data as the previous plot, but if you recall, in the Nevada plot, here we go, is January and February in their second and third month had a lot of failures. And let me get a red color here, see if this will work. Oops, that's going to give me a box. I don't want that. Get my pen back. The second and third month had a relatively high amount of failures. The development team got called back in, or the manufacturing team. Somebody said, hey, this is way too many failures early on, and do something about it. So there was investigation, all the normal things were done, root cause analysis. And then as they started shipping in March and beyond, they had some design and process changes that would address those early failures. And in this particular case, the question was, well, did the changes make a difference? Did they improve the reliability performance of the product? So let's go down and look at the plot where we're looking at just the January, February data, which is this blue line, and it has a characteristic early life failure behavior. Beta is much less than 1, and the rest of the data shows a very different behavior. There's fewer failures early in life. There's less of a chance that they'll fail. So instead of having a for almost 5% chance of failing the first month. It's 0.7% chance of failing in the first month. That's a pretty good improvement. This difference was noticed within a couple of months of shipping the new design. But we didn't address the wear-out mechanism. It wasn't apparent. We hadn't gotten to these failures with the existing design. We fixed it after 3 months. So 1, 2, 3, right here, the fix went into place. And so the units that are along this line include the design improvements that eliminated a good number of these failures. Well, what happened though is that the curve just rotated to a steeper slope. And one of the outcomes of that is the characteristic life got worse. So if you're only tracking MTBF, it would look like the improvements you made, the real measurable improvements in the early life phase of the program or of the deployment, would appear as decreasing the reliability of a product. But it's not just the single point, not this where it happens to be the 0.63 failure rate. It's also the slope of the curve. And so once this plot ran out a couple of months, they saw the change in the improvement, but also the change in slope, and realized that at about a year, this new failure mechanisms would increase the amount of failures they're seeing. So it would follow closer to this line than the previous one. And so they could judge that at 2 years they would have, so 24, 40% failures. Now, if that's acceptable, drive on. If not, what can we do to address the failures that are occurring and shift this curve over to the right some more and or change its slope? So using the simple data, breaking it up just into before and after a particular change, we can see the difference. That's a good use of a distribution. But we can also do projections and get rough estimates what's going to happen in the next couple of months. These are all pretty useful type things that can occur to us. Types of questions we would have to answer. So here's an example, is that once I have some data and I fit a distribution to it, I'll use first an exponential distribution and then a Weibull distribution to do some calculations. And it's another way to use the distributions, not just graphically, to see where we're at. So let's say you got 500 units put into the field and they operate for a year. The ones that failed are repaired fairly quickly and put back into service. And we've had 30 failures overall in that year. So if we work with an exponential distribution and we're interested in what's going to happen in the second year, we can do a very simple calculation to figure out first what's the failure rate or the MTBF value by tallying the number of hours that the 500 units operated. Let's say they all ran all year, 24/7, and that would be close to 4,380,000 hours. Well, divide that by 30, and that gives us our average time to failure, the MTBF. So this f of t here is the cumulative distribution function. It's commonly used capital F of t, the probability of failure at up to some point in time. And the formula for the exponential is 1 minus e to the negative lambda, or e to the negative t divided by theta. So put in some numbers, and in this case multiply by the 500 units, I end up in the second year getting 29 failures, 30 failures, which is as expected because I should get about the same number of failures as I did in the first year. It's one of the features of an exponential distribution is it doesn't really remember how long a unit's been operating. It works on the principle that every single hour it has an equal chance of failing. And that's what this MTBF value is calculating. It's a 1 in 146,000 chance of every hour that this unit would fail. So if we start 500 units and run them for a year, we would expect about 30 failures. That's okay. And if the actual failure mechanisms behave and fit a exponential distribution, this is fine. What if they don't? What if the beta value is not equal to 1? So let me once again clear out my previous annotations. This little step here is a feature of having to re-record this. So let's say, for the sake of argument, that our data actually has a pretty pronounced wear out mechanism or early life failure behavior. It's a decreasing failure rate. So we fit the data. Then we use the same f of t, but this time for the exponential or for the Weibull distribution, which includes a beta exponent. Now when that equals 1, it's identical to the exponential distribution. But in this case, we're accounting for the rate of change of the failure rate. So 0.5 here shows that there's a very gentle slope, a shallow slope, and the chance of surviving the first year is less than the chance of surviving the second year. So running out the calculations, at the end of 2 years, we would have 42 failures. This does remember what happened the first year. So I have to include the first years of hours in the calculations. And then I subtract out the failures that occurred the first year. And I find that in the second year, I would expect less than half of what I got the first year. It's to be expected. And that number will continue to decline until either a different failure mechanism starts to dominate the time to failures, or I run out of units. But that's one way to calculate it. The converse, let's say I have a increasing failure rate, and that's those units that we had after the change for the early life failures, we had a product that was wearing out. So in this hypothetical situation, we fit the data and I get a beta of 2. We get a characteristic life. Think about the term for a moment. And then run out its calculation. And as expected, we're going to get way more failures the second year than the first year. So once I know the distribution, I'm making the assumption that the shape of the distribution, the slope, and what's behaving on it, what's failing, will stay relatively constant, or consistent, I should say. We can make these rough predictions. So if our warranty period is 2 years, we could use this in the first year, then project what the second year's costs are going to be. If we're doing spares, we could use it for that kind of realm. But it's also something that comes back to the development team for process improvement. Are these meeting our objectives or not? What can we do about it? So it's a couple ways, calculating ways, that we can use the distribution data. So we take data and fit a Weibull or log normal or exponential normal distribution, whatever is appropriate from that regression process. And then we can answer questions about the data. How many will fail in the first month, for example, of use? That's one way to do it. Those that have seen my other work and other presentations know I tend to advocate avoiding using MTBF. And I will acknowledge that if you can show that it's appropriate and you're using an exponential distribution, it's fine. But even if you use the term MTBF, if it's coming from a Weibull distribution, which it's possible to, you should say that. And then what are the parameters that because eta is not the same as MTBF when you have a slope other than 1. It could be from a log normal distribution, any distribution. But if you know that, use it and use that to do your calculations. Don't simplify your data to an MTBF value, which then in the calculations forces you to have made the assumption that it's a constant failure rate. If you know it's not, don't use MTBF. Vast majority of cases, it's not a constant failure rate. All right. Now, I haven't spent too much time on the attribute data, the pass-fail kinds of systems. If I am, and one of the most common questions we get is, um, are we going to have what's the sample size? If I don't know how many different ways that can be asked, but it is often very direct. The program team will say, we need to plan for samples for testing. How many samples do we need? How many samples we need for life testing? How many you need for environmental testing, so on. So some of the tests we run are based on pass-fail criteria, and as far as I know, one of the most efficient ways to get a sample size is to plan on no failures. Is run the test such that if you get no failures, it gives you a conclusion of some level of reliability and confidence. But if you're using standards like IEC standards or JADEC standards to design your testing, you'll commonly see the 77 samples. And there's a few other what I call magic numbers. But why 77? What makes it special? And for some products, it's just unreasonable number of samples. But in the integrated circuit and digital logic world, it's very common to see test results with 77 samples from 3 lots, and they all pass. But what does that really mean? So if you do a little bit of algebra based on a binomial distribution sample size calculations with 0 failures, that's, in other words, a success test, we can get n, the number of samples, is the natural log of 1 minus the confidence. Confidence being C here, which is the type 1 confidence, the chance that our sample is not representative of the true population. Or I should say is representative of it, because we want a high confidence that, say, 90%, means that 9 times out of 10, our sample is going to give us an answer that's close to the actual answer of the unknown population. M in this case is the lifetimes. So if I am creating a product that's expected to operate for 5 years, the testing that I'm doing should replicate the stresses equivalent to, or actually, the 5 years. Beta is from the Weibull distribution. That if it's a beta, say, of 2, and I can run, say, 2 lifetimes worth of cycles on a product to accelerate the stress on it, it gives me a 4x reduction in the number of samples I need. So it comes important when we're doing something other than just 1 lifetime. But it's part of the calculations we can take advantage of based on how often we expect to see failures. And the beta is an indicator of that. R being the reliability, how many should survive 1 lifetime. So for example, if I have 95% confidence that I have at least 96% reliability, the test was run for one lifetime, I need 77 samples. So 95, and it's rounded up just a little bit, gives us this magic number of 77. Now, I don't know about you, but if my 95% confidence is great, that's no problem. It's the 96% reliability that they're demonstrating or showing. So it's saying that if there's no failures, I'm at least 96% or better. Now, most ICs are much, much more reliable than that over a reasonable lifetime. But there's no reason to go to higher samples because it passes, and people are happy with when tests pass. But this estimate, demonstrated value for the reliability, is pretty bad. If my computer, if every component had this value, it'd be surprising that it would work a week. In your system, when you look at your ASIC, floating or a FPGA or other significant chip, it might be the least reliable part in your product, but is 96% reliable good enough? Probably not. So the other thing we see is 60% confidence. So given that previous formula, it also, by lowering it from 95 or 90, it lowers the number of samples we need. But what does it really mean? And Thomas here talks about that it's um, uh, the true MTBF. I would translate that to the result. The reliability is somewhere between this upper and lower values. Not exactly, no. It means that that particular test we did is um, only going to represent, is likely to represent the actual population only 6 times out of 10 that we run this test. We don't know on any particular results if it's appropriate or not, but we have a 60-40 chance of getting the wrong answer, getting a misleading answer, where it could pass when it really shouldn't, or it could fail when it really shouldn't. So the confidence is the risk that the sample doesn't represent, or in this case, the risk that the probability that the sample represents the unknown true population. The lower the number, the lower samples I need, which is great if you're running testing, but it also increases the amount of chance that the test is pretty meaningless. So 50-50 is a coin flip. There's really no point, in my opinion, of running that test. But higher confidence is a statistical sampling risk. If your product's really good, yeah, it still takes more samples to show that it's really good. Reducing the confidence is an artificial gain because it also increases the chance that you'll get a bad result. A misleading result is what I mean by bad. So take a look at your data sheets and your vendors' information about how they qualify their systems. If they're using success testing, well, what does that really mean to you? One is the test conditions related to anything related to the lifetime of use for your product. So how would you have to modify that M value to, if they do 1,000 hours and they have a 10x acceleration factor, that's 10,000 hours, how does that relate to lifetimes that you expect it to run? That would then give you a value for that M value. But also, what's your target? How reliable do you need to be? And can you get there or not? If they use 60% confidence, how do you translate that to a reasonable confidence level? Or how do you quantify the risk that you're taking that the answer could be wrong? So take a much closer look at how your vendors are doing the qualifications, and where possible, relate what they actually do to your conditions and see if you can translate their results through either a physics of failure model or a acceleration model to your particular conditions. And then sample size and the distributions then give you a sense of when you should expect the early onset of failures. So one more example, and this is a bonus that wasn't in the live presentation because I ran against my hour, but being a recording, and if you're still interested, here's one more example of a distribution. It's not as common as normal or Weibull distribution, but it is pretty handy, and it answers a particular kind of question that I once ran into. And so we had a set of components from a vendor, a large vendor creating this product for, and I think they'd created it, tens of millions of these units and of this family of product. But it was new to us, so we did some testing, and the vendor and us agreed on the type of test, and we were concerned with a condition called black plague. And it's a metallization issue that creates weak solder joints and weak bonds. And so conducted this test on 30 units. It was basically a desire to check if this risk was real or not. But we had 15 out of the 30 fail. So the vendor came back and said, well, wait a second. We have lots and lots of test data that shows, and field history that shows we have a 100 failures in time or failure rate. It's the 100 per 10 to the ninth hours of operation. So it's basically a 100 per billion failure rate. So that didn't really fit our experience in the lab very well. Some of the testing they did would be related to this particular failure mechanism we were seeing. The test was done well. They agreed the test was done well. And so my boss at the time said, so why did we get 15 failures when there should be less than 100 failures total because you haven't made a billion parts? And so they replied pretty quickly and said, well, it was just random chance. We picked 30 units to ship to you without any particular um, care to pick perfect parts because we knew it was a very good solid part. So it was just random chance. There is a probability that you got 15 bad ones out of 30. And so that's where the hypergeometric comes in. We can calculate that. So this is the probability of getting exactly 15 failures in the 30 samples we took from a population that should only have 100 failures per billion. And so we did a quick calculation using this, and it gives us roughly 8.5 times 10 to the negative 98th chance of seeing 15 failures out of 30 if the true population was as good as they claimed it to be. So we wrote this up, and my boss asked me, and I concluded it with this seems highly unlikely. And my boss wondered what was impossible if I had to get up over negative 100 before I changed the adjective there. But the notion is that, yeah, there's a random chance, but I have a much better chance of winning the lottery than I've seen 15 out of 30 fail just by chance. So we ended up spending some more time and effort on this and found that it really was a metallization problem that was a latent defect in all of the existing products they'd shipped. And in conditions where there's a little bit of vibration, some thermal cycling, these packages would fail. And so we ended up doing some more work to find a suitable solution. But instead of accepting that this is just chance, do the calculation, figure out what is the chance that this would really occur. Now, if it would have been a 50-50 chance of 0.5 instead of such a small number, it would be believable. We could accept that. Even if it was 0.1, a 10% chance, that's in the realm of it could happen. But one per, I think it's a Googleplex number, is pretty rare. So it casts some doubt on the claim that it was just random. Well, there's lots of other uses for distributions and life data analysis. Those are just a couple of examples that I've seen in the past, and I know that there was a handful of others that were chiming in on other uses for this. But it goes from sample, we need to know the life distribution to get an accurate sample size calculation. To design an accelerated test, we make assumptions about the failure life distribution. To interpret test results or interpret field data, we often use distributions to do those things. So it's a tool that we have that's got incredible flexibility and helps us understand that pile of data that we gather. Even with all of its issues, it gives us a glimpse as to what's going on with the systems that we're dealing with. So with that, I'm going to conclude the recorded session of this. And if you have any questions, please let me know. Let me bring up the, I think I have, yeah, there's the download tab is there, so you'll be able to get the slides if you want them. A handful of other comments. One last note, still continuing with the Dare to Know interviews. Tim Rogers and I are interviewing thought leaders in the reliability world right now, and we're posting those to the Ascendo reliability site. Those recordings are available there. I need to find some time to get those posted up on iTunes as a podcast. I think it's going to make a nice application for that. But take a look at those. Let me know what you think. And if there's anybody that we should be interviewing, let us know. We'd like to get them on the agenda and get those interviews conducted. So if you have any questions, considering I'm not live at the moment, feel free to give me an email or send me a message through LinkedIn or Twitter. I'm pretty active on both of those. And let me know what your thoughts are. Also, I saw a handful of comments here of future sessions, like on confidence intervals, on sample size, on more on the distributions and the use of these different distributions and the different functions that we typically use, the PDF, CDF, reliability and hazard function, topics like that. So I've got one more planned for next month, and then after that I'm going to be developing other topics. So if you have any ideas what you'd like to talk about, please let me know. We'll get it on the calendar. So with that, thank you very much for listening to the recording, and we'll see you next month.